Hello, everyone, and welcome to another exciting episode of York Observatory, that is the Alan I. Carswell Observatory TeleTube. We broadcast every Wednesday night at 7:30, and of course, this Wednesday being no different, we have a wonderful program lined up for you. So tonight we're going to be looking at an amazing part 2 from Professor Jesse Rogerson, our first ever two-part talk, as it were. So I hope you enjoy the lineup here tonight. And I'd just like to give a shout out to Amin and Prayosha, who are joining us for the first time as crew on TeleTube. So welcome everyone to another exciting Wednesday. Of course, this Wednesday, we do have a little bit something extra special planned. We are going to try to be showing live images from the 1 meter telescope here on campus at the Alan I. Carswell Observatory. So I'm just going to hop over very quickly before we get started with our main event. And we're going to actually be able to just have a look really quickly at the planet Jupiter. So let me just go ahead and capture that for you very quickly here. All right, so I've just switched over. Hopefully everyone can see. This is a live image of the planet Jupiter. So Jupiter is pointed in a little bit of a different direction than Mars. We are fighting some very big clouds here at the moment. So I have had to point in a different direction. However, Jupiter is also a very interesting planet. As you can see here, it is a bit hazy. There are some very large clouds in the sky at the moment. I'll just see if I can make this a little bit bigger for you here. And this is what the planet Jupiter looks like right now through the 1 meter telescope at the Alan I. Carswell Observatory. This is coming directly from our eyepiece cam, a mail-in cam. So this is pretty much what you would be able to see if we could get you up to the eyepieces. Of course, we are unfortunately not able to do that at the moment. So we have the next best thing is live images streaming directly to you. Now, we have a couple of interesting things about Jupiter, which might theoretically lead into our talk today. Of course, Jupiter is in our solar system. It is the largest planet, and it is a gas giant planet. We are not getting the best possible view of Jupiter, but this is actually pretty good for a live image. A lot of the images you see from NASA and from other telescopes, and including ours, are actually taken with a CCD, and many, many, many images like this are combined to make one very, very sharp one. I'll just go ahead and throw it open to if there's any, I believe our speaker today, Professor Rogerson, you had a quick comment about Jupiter you'd like to throw in there?
Oh, I just read, thanks for letting me throw this in. I just read that Jupiter has a new storm. I mean, it has like a million storms on it. Obviously, the Great Red Spot is the most iconic, but there's a new one, a quite large one in the northern mid-latitudes that may or may not, depending on how things go, rival the size of the Great Red Spot. So that was, I think, the end of August or mid-August, those observations were showing that a new storm, a big storm had erupted. It's kind of interesting.
Oh, absolutely. And there's all kinds of interesting news coming out of Jupiter at the moment with the new Juno spacecraft mission that was recently looking around Jupiter. Jupiter is one of the few other planets in the solar system than Earth that we know has lightning. So lightning strikes have been observed on Jupiter, but it's not quite like Earth. It's not striking to ground. As far as we know, Jupiter doesn't have a ground, so it's actually inside the cloud layers of Jupiter. It is an absolutely fascinating planet, and well worth a look. So I'm just going to try adjusting a little bit. We are getting some more clouds coming through, so I'm not sure how many Jupiter images we'll be able to get tonight. Oh yeah, it is keeping, we are battling quite a few clouds. I don't know if you can see Jupiter anymore, but it is just the faintest little blobby blob now. Let me just try moving over to Jupiter's neighbor, Saturn, which is quite close to Jupiter in the sky right now. Before we do that, Quentin, you have a quick little fun fact about Jupiter's cloud layers?
Yeah, speaking of clouds, one interesting fact that I learned the other day is that Jupiter's cloud layers are only 50 kilometers thick. So all of the storms and all of the clouds and all of the bands and the surface, quote unquote surface features that you can see on Jupiter are just part of a couple cloud decks that only go down 50 kilometers, and below that it's just hydrogen and helium, all the way down to whatever more dense layers are believed to exist below that. So I remember thinking it was really interesting that all of those storms and stuff are in a section of the planet that's only 50 kilometers thick.
That is super interesting. And, as you can see, we are also battling clouds here. Sort of as we're speaking, the clouds are coming in and out around. And if you notice that the wiggliness of this image, how it appears to jump about, that is in fact due to our atmosphere. So Earth's atmosphere is one of the big problems in observational astronomy. Cloud layers here are preventing us from seeing cloud layers over on Jupiter, as it were. As you can kind of make out in between the clouds here, we do get a good view of the bands of Jupiter and some of those storms mentioned by Quentin and Professor Rogerson. All right, we are going to go and hop over just to see if we can get to Saturn. And for the curious, let me just see if I can adjust this here. Just in case you haven't seen the telescope move before, I will just adjust this. Now, this is actually how we move the 1 meter telescope. We have a little set of Arian declinations with a bunch of different stars and objects mapped out. And what I can do is I can select an object and then tell the telescope to go there. So right now we're at Jupiter, and if I move a little bit to the side, we'll try going to Saturn. Maybe there's a little bit less clouds over here. So now I'm just going to tell our camera that we're on a new target. Oh, it seems to be more clouds. Oh no. There are an awful lot of clouds in the sky at the moment. I don't know if you can tell, but Saturn is just starting to peek out of the edge there around the clouds. I'll see if I can zoom in a bit for you. So you can just see the rings of Saturn. You know it's cloudy when you have trouble seeing the brightest objects in the sky. Of course, the very, very brightest is Mars, which is up rising in the east at the moment, still a bit too low for us to aim at in this teletube. Well, not right now, but at the end, if it's clear, we'll totally go there. just to clarify, so people aren't worried. We will keep an eye on the clouds sort of as the broadcast continues for the main presentation tonight. And if I can get a clearer view of Saturn, I will put that up for you all. So Saturn, much like Jupiter, in case you didn't know, is also a gas giant planet, but it's much less dense. It is number 2 in terms of the size. And it has the beautiful, beautiful ring system around it, which we can just barely make out from the clouds here on Earth. On a very clear day, we would be able to see a little bit more structure in the rings and perhaps even a little bit of a shadow between the rings and the planet. And just as a little reminder, this is what we would see through the eyepiece at the moment. You'll notice a lot of the color is kind of been pulled out of the image, and this is mostly due to clouds. Alrighty, everyone. So this was Jupiter and Saturn to get our appetites whetted. Hopefully those clouds do clear. As you can see with optical astronomy, we are a little bit at the mercy of the weather systems. Oops. I'm just going to pull myself back here to the right screen. And we'll go ahead and start with our regular scheduled program, as it were. For today, we actually have an amazing talk planned, and actually it's even better than that because we haven't planned it. Professor Jesse Rogerson is here, and he has planned it. So I'm going to go ahead and end off this very long intro that I have been working on. And Quentin, would you like to give a quick introduction for the crew tonight?
Good evening, everyone. I'm Quinton, and I'm here with Amin, Prayosha, and Shannon, live from the Alan I. Carswell Observatory at York University. Tonight, we've got a great presentation about interstellar objects Oumuamua and 2I Borisov by Professor Jesse Rogerson from our very own York University.
All right, welcome, Professor Rogerson. If you would like to turn on your camera, as it were.
Hello, everybody.
In here.
Sorry, what was that?
All right, great to have you on tonight. And I do have to give you a new introduction. So this is a new TeleTube. In case you missed last week's TeleTube, we have Professor Rogerson back again tonight. This is a special double feature, part 2, as it were. And this is going to be about interstellar objects, in particular, some very, very cool and strange ones. So I'll let Professor Rogerson tell you all about that. But first, let me give a little bit of an introduction in case you haven't heard of him. Professor Rogerson is here at York University in the Department of Physics and Astronomy, a bit of a new professor. We're very, very lucky to have him. He actually used to be over in the Canada Aviation and Space Museum, part of Ingenium, Canada's Museums of Science and Innovation. He was over there for about 3 years, building exhibits, writing blogs, doing program development, and apparently even made a Nintendo Switch game. Professor Rogerson can be found on Twitter at Jesse Rogerson. So that's the name all spelled out. And he's going to tell us about all kinds of great things from interstellar objects, and maybe not the Switch game, but I would love to hear about that later. So welcome, Professor Rogerson. It's great to have you on again.
Thanks for having me. Yeah, it's good to be back. Okay, so I should steal the screen, I guess.
Yeah, you go ahead and take it away.
All right. So people can see this now. Okay, cool. Yeah, it's good to be back. Thanks for having me, Dr. Hyde. I was really enjoying watching you find Jupiter and Saturn. So I mean, this is probably what got me into astrophysics. When I look back at it, there were moments where I was doing my undergrad. When I started my undergrad, I was in computer science, and I didn't like it. It wasn't clicking with me, and I found myself in astronomy. And I remember the first time I saw Saturn through the telescope. That I was like maybe, I want to say I was like maybe 19 or 20. So I didn't come at this from a young age. I stumbled into it in my undergrad, and when I saw Saturn through the telescope for the first time, it just blew my mind, and it still blows my mind every single time I see it. So when you pointed at Saturn there, and like the rings and the planet in the middle, it's just like you feel like you can reach out and touch it. So that's super cool to see. All right, so I get to tell you a little bit about a scout from distant lands. So I'm not, okay, so just a disclaimer, I'm not a solar system astrophysicist. So I'm not a planetary scientist. The research that I've done with my PhD is on quasars and supermassive black holes. So when I do research and write papers and use telescopes, I'm looking at supermassive black holes really, really far away. But I found this topic to be quite interesting because it's sort of universe shattering in a way. It changes how we view the solar system that we live in. It changes how we view the universe. And so I put together a little talk about that idea that our view of the solar system and our view of the universe or the galaxy has changed. Okay, so all of this starts, so this is an artist's impression of what we're going to be talking about, but all of this starts with this picture right here. Okay, so this is a picture from a telescope called Pan-STARRS, or a survey called Pan-STARRS. And this is the discovery image, and I'll get to exactly what this is. I'm sort of like teasing you a little bit about what it is. This is the discovery image of the object. It was moving rapidly across the sky at about 6.5 degrees per day. So I think if I did my math right, I think that is about half as fast as the moon moves. So if you watch the moon, if you took a picture of the moon, or if you went out and you looked at the moon and marked where it was in the sky, if you came back the next day, it would have moved quite a drastic distance, because the moon moves very fast around us as compared to other things in the sky. And this thing was moving pretty quickly as well. And so in 4 images on October 19th, 2017, so that's 3 years ago, these images were taken. And what you're looking at here is it's a reversed image. So space is this stuff, and stars are these things right here. And there's this elongated thing that's moving through the sky. It's like the shutter was left open for a long period of time, and the light reflecting off whatever this thing was came into the CCD chip, but was recorded on multiple pixels as it traced across the sky when the stars were not moving, because the telescope was moving with the stars. And these big red things are bad columns and bad pixels and stuff that they've masked out. Okay, so Pan-STARRS. Pan-STARRS here is, well, it's technically 2 telescopes, but the main telescope is this one. It's a 1.8 meter RC telescope. Its first light was 2006, and it's on the summit of Haleakala in Maui. That is I think it's the island just next to the big island of Hawaii. It was/is the largest digital camera with almost 1.4 billion pixels. This camera is massive. I'm not sure if that's still the record, because the Vera Rubin telescope is coming online eventually, and it's got quite a camera on it. So this is where it's located. Yep, right next to Hawaii, the big island of Hawaii there. And these places are really good. The summits of these mountains in the middle of the ocean are really great places to do observing. I believe that, so that one telescope, this one telescope here is one of them, and I believe they finished construction on a second one, but I can't get a lot of information on whether or not it's fully operational yet. I think they're still commissioning it, and I think there's 2 others planned anyway. So the point of this telescope is to survey the sky, the entire observable sky from that location, Haleakala, and get an image of the sky, a full image of the sky, once every 10 days. I believe they were attempting to go a bit quicker, but it worked out to be about once every 10 days. So that's a lot of sky. That's like this much sky. This part is not visible to them, but this would be the amount of sky that they would cover in a night. So it's about 1,000 square degrees per night. So that's a lot of imaging to do. And after their first data release, they found, by over and over and over again looking at the night sky, they found a whole bunch of asteroids, a whole bunch of things moving through the sky. Because what you do is you keep taking pictures of the same spots of the sky every 10 days, and then you just go back and you compare. Has anything moved in those images? And all of these things, as you see on the screen here, have moved. And once you see them move, you can calculate their orbits and determine what they are. And these are the asteroids, 250,000 asteroids discovered. That's incredible. These ones were the potentially hazardous ones. So if you're worried about things hitting you, well, there's ones calculated out there to be potentially hazardous. None of them have any high probability of hitting us at the moment, but they're things we need to be aware of. But that's not the point of this talk. And they have put out a couple of data releases, Pan-STARRS. I'm not going to get into that, but they're hundreds of thousands of images, hundreds of millions of objects cataloged. One of the most incredible images of the night sky, completely stitched together. Really, really good stuff. And it's all available for free if you ever wanted to go through it. Okay, back to this. So Robert Verk, he took these 4 images, or at least was looking at these 4 images, and labeled it a comet, actually. Comet 2017 U1 was the name that it was given at the time. And those things are stars right there. And what they did then is that they calculated where it was moving, and determined how fast they needed the telescope to move to keep track with it, and took more images of it. So this is what the Canada, France, Hawaii telescope did. And so they got it. That's the C 2017 right there, thinking it's a comet. And then there's the stars. These are the stars that originally were in the other image. But after getting some really good images of it, they thought, it's not a comet. It doesn't have any cometary tail on it. So if it doesn't have a tail, it's near the sun, it's probably an asteroid. Okay, great, it's an asteroid. So then they started calculating the orbits, and this is where things get really interesting. So you can, by knowing where it's been on the sky, you can calculate where it's going. And this is sort of similar to what you do if you ever play catch with someone. When you see someone way on the other side of the field throw a ball at you, your eyes immediately start doing calculations. How fast is it moving? How quick will it fall towards the ground? And you move to the spot to catch it, right? You make a prediction. And this is what we do in astrophysics as well. You can make predictions of where things are going to be. And the orbit that was calculated for this object had a velocity that meant that it was leaving the solar system. It was going faster than the sun would be able to hold on to it. And if we look at, and this is an animation of it right here, of the orbit that it took, it swung through the inner solar system and started heading out. So this was a huge discovery because this had never been done before. The fact that this has an escape velocity, it's going faster than the sun can hold on to it, means that it must have come from outside the solar system. There's no way that something that originated here, bound to the sun, could ever get enough energy to leave in the way that this thing was. So this thing, just by purely calculating its orbit, we can determine that the way it came in, there was no way for it to have been bound to the sun, and now it's on its way out. So it's swung around, going out. This is the first detection of something that came from outside the solar system, or an interstellar object. And then what they did is they started pointing, every telescope on the planet started looking at it and getting images of it, and calculating the brightness of it. So what you're looking at here is the brightness. This is we use the word magnitude in astronomy, but this fainter here and brighter here. And I know the numbers go in the opposite direction, but that's what us astronomers do. And so what you're looking at here is that there's quite a large change through time. And there's the VLT is a certain telescope. Gemini is a different telescope. We can go down this list here. Keck is another telescope, CFHT again. And the colors that you're looking at are different filters, looking at it in the G filter, the R filter, the I filter, and so on. And you can see this is an object that is getting really bright and really dim, really bright and really dim over and over again. And if it was a perfectly spherical thing, then we wouldn't expect it to have any change in brightness as it spun or as it did anything, right? It would just be, if it was a perfect ball, then it wouldn't be doing anything major. But something that has that shape, actually, you can simulate weird elongated things can give this shape. So what astronomers started realizing is that this thing is probably an elongated thing, okay? And cigar shape is a common thing that they would call it. And this is the artist's impression that I showed you before, that this object that came flying in from the outside the solar system has this really weird shape, probably between 100 and 1,000 meters long, and then about 1/10 of that wide. So it's a really, really weird thing. And they had to rename it because they were calling it this asteroid 2017, but no, we had a new designation that was created for it, the letter I. So instead of C or A, comets or asteroids, this is now an interstellar object. They named it Oumuamua, and this is Hawaiian, and the first part means to reach out for, and the second part, mua, and said twice for emphasis, means first or in advance of. So it's another way of saying it, a rough translation would be a scout or a messenger from a distant area, distant past, or a distant land. So where did it come from? Well, they calculated where it came from, and these are the RA and the DEC of where the orbit traces back to. Lyra, roughly about 5 degrees from Vega. But Vega wasn't in that position when Oumuamua was there, so it probably didn't come from Vega itself, so we don't really know. Where is it going? It's heading towards Pegasus. That's the RA and DEC right there of where it's heading to, and you can point telescopes at that and see where it's going. Can we visit it? No, we probably can't visit it. It'd be really difficult to catch up to it right now, and I'll explain where it is near the end. But there were two surprising conclusions and observations made from this. The first, there was a non-gravitational acceleration. Okay, so what you're looking at here is this sort of animation of Oumuamua coming in, And then it reached this, as after it had passed by the sun, what its expected trajectory was different from what we were observing it. So basically, like I told you before, we can calculate where we think something is going to go based on the gravity, based on how fast it was moving, based on what it was doing, what its orbit is telling us. So we can say, okay, this is where we think it's going to be. And then when you go back and you look at it and you find a different orbit, that means something is awry, something is, you're not calculating it properly, or you miss something. And the solution to that is that it probably actually was outgassing, that there was some material that was outgassing like a comet, which was providing a bit of acceleration. It was getting a little bit of a kick, almost like it had like a little bit of an afterburner on it. And that accelerated it and changed its orbit. So they actually changed it back to a comet, an interstellar comet, but a comet nonetheless. And the other secondary conclusion that came from this, which is super interesting, is the number density. So once we find an interstellar object in our solar system, something that originated from outside the solar system, people start making some guesses about how many should there be. So this makes me think way back to before we knew about planets outside of our solar system, exoplanets. Before we found them, it was anyone's guess. It was like, there could be millions of them, or there could be none, or we don't know. But once you find one, you can start doing better estimates. And when you find more, you can do even better estimates. And when this object was found, Oumuamua, back in 2017, people started making estimates about how many objects they think we should see. Here's a really interesting one. Any one time, there are close to 10,000 interstellar bodies similar to Oumuamua between the sun and Neptune. And like, that's a lot of objects. Another estimate suggests that there could be always one about 250 meters in diameter interior to Earth's orbit. Like, that's mind-blowing. That's saying that there's always one of these hanging around. So it took this Pan-STARRS survey that was viewing the sky over and over and over again to find it. But that was back in 2017. Interesting enough, just like the prediction said, we did find another, and that was this one. So this is an image here of 2I Borisov, the second interstellar object, and it was discovered in the summer of 2019, just over a year ago today. So here is its trajectory. It came flying in from above the solar system. It didn't get as close to the sun as Oumuamua did. It got to within about 2 astronomical units, so just a little bit outside of Mars's orbit. About 500 meters in size, roughly the same size. So here's the really interesting thing that happened to this one. So it was immediately obvious. You can look right back here. This is obviously a comet. It's outgassing. The other object, Oumuamua, was not outgassing, or at least not visibly. We didn't notice it. We could measure that its trajectory is changing, but we couldn't see it. This is obviously outgassing, very, very different. We can say it's a comet, and we can say that it came from outside of the solar system. But what happened after it swung by the sun, I suppose that it heated up a lot. It actually started falling apart. And this is a series of images that were taken actually relatively recently. I think March this year, these were taken. And so this is, they're all false colors, but it shows you the coma of the comet. There's the dense nucleus there. And then there was some weird event that happened that caused this little chunk right here to go flying off. And they think that they've seen a couple events, 2 or 3 events of the object falling apart. And so what you're looking at here is an object that got heat up by the sun. Volatile gases inside, like water or CO2 or ammonia gas or whatever, volatile chemicals turned into gas because they got heated up, and then it started breaking apart. And comets do that sometimes. They do that here. What's weird is that didn't happen for Oumuamua. And so what I want to say for these 2 objects is that we've had now 2 interstellar visitors, interstellar objects that came from outside the solar system, originated around other stars, and we've seen 2 completely different things. The Oumuamua was a weird cigar shape that was kind of a comet, but not really a comet, and it was very dormant. And then we see 2I Borisov that came through and acted just like every other comet we've ever seen, and started breaking apart as it is now flying out of the solar system. Just to give you a sense of where these things are, Borisov is at 7 AU right now, so that's not quite as far as Saturn. And Oumuamua is almost at Uranus, I believe, roughly around the orbit of Uranus. And they're heading out and they're not going to come back. And I think that puts me at about 15 minutes, and I'll say thank you. And that's all I got in interstellar objects.
Wonderful. What a great topic. So we do have time for a few questions, of course. I'm just going to, I think we'll leave it on your screen in case there are any questions relating to your slides here.
Sounds good.
But I'll go ahead and throw it open. If there are questions from our YouTube audience on this talk, please feel free to post them, and we will try to ask them to Professor Rogerson here live. So in the meantime, while we're seeing if questions are coming in, I know that a few of our crew here also have questions. Now, Amin, I think you were up for sort of the first question of the night, if you'd like to go.
Okay, so my question is, why is Oumuamua so elongated compared to other objects in space?
That's a great question. So this leads to why it also wasn't outgassing. So it seems like it might have been part of a fracturing object. Now, let's assume that it's a comet as we know comets to be. And when it gets close to a heat source like the sun, it should outgas. All comets do, but this one didn't. So this one either has low amounts of volatiles, or perhaps has some sort of is compressed so much, or some sort of molecular change that wouldn't allow it to outgas as much. Now, I can't really say for sure. I can speculate only, but it perhaps was part of a collision of some kind, and a collision created this weird shape. But it's hard to say. And to be honest, it might just have a weird reflectance. We don't really know. We can't really resolve what this object looks like. We're basing this off of the light curve of how it changes through time. It gets brighter and dimmer and brighter and dimmer. It's possible that it is not as elongated as we say it is, and that we're making assumptions of the reflectivity of the surface that we shouldn't be. So it might not be as elongated, but weird lumpy things are in our solar system too. Like if you know the comet 67P kind of looks like a weird potatoy duck thing. There's weird objects out there, and this just is one of them, I guess.
Great question. All right, we do have a few coming in from the YouTube chat as well. Of course, there's
Awesome.
one by what speed are these objects moving?
Oh yeah, good question. I didn't say the speed, did I? Okay, I have that written down somewhere. Okay, so Oumuamua incoming and outgoing speed, 26 kilometers per second. That is 93,000 kilometers an hour. That's super fast.
That is super fast. All right, so going very, very, very quickly.
Oh, sorry.
Yeah.
Just to caveat that, that's its incoming and outgoing speed. Its fastest speed when it whipped around the sun. So when it's coming down from above the solar system, it's speeding up. It's falling down a hill. When it gets to its fastest, right when it whips around the sun, that was over 300,000 kilometers an hour. It was going real quick.
Exactly. Slingshotting, if you will, with gravity. All right. Now, next question is from Harrison on Borisov. Could it be part of a normal cycle for it to break apart and then over millions of years in interstellar space to recombine if the pieces travel together?
Oh, that's an interesting question.
Yeah, I like that one. It's a good one.
So based on my understanding, okay, so the object that fell off of it would have to not be at escape speed. I don't know what the object is doing that fell off of it. I know that from experience that the object Bennu, so the asteroid Bennu has had these ejection events. I don't know if anybody has seen those before. There's a OSIRIS-REx, which by the way, a York University professor by the name of Mike Daly is a part of that mission. So we have a spacecraft orbiting an asteroid right now called Bennu, and Bennu is like ejecting things off of it, and they're trying to figure out exactly why that's happening. Anyway, the point is that not all of that stuff that ejects off of it goes away. Some of it or most of it falls back to Bennu. So based on that, I would say that for Borisov to have this event where it's sort of disintegrating, it's possible that a lot of the stuff that disintegrated could come back to it just through gravity. The scale of those images, so if I go to these images here, where is it? That is probably quite a large distance, and that's quite reflective. So I'm betting that the biggest pieces are not going to come back, but there's probably a lot of little stuff that will. And I wouldn't call it a cycle. I would call it sporadic, random explosions. There's two possibilities. One, the sun heated it up and it started exploding all over the place with volatile gas. The other one is that it could have a weird spin, and the spin helped with the stuff fly away. Some of it could fall back, but it would all be random. I wouldn't call it a cycle.
Exactly. I totally agree with you on that one. And it's, if you want to think about it a little bit, if it broke apart in such a way that the pieces were traveling together, you might kind of have a rubble pile scenario, which is actually something we do see out in the asteroid belt, where things kind of get close enough to roughly be together, but they're still not necessarily going to recombine into anything. So it is a very interesting question. So I'm glad it got asked.
Yeah, really good.
All right, so we have time for a couple more.
Sure.
So let's see here. We have a couple more about these crazy interstellar objects. One from Byron. Is the composition of these ISOs similar to asteroids and comets we've monitored in the solar system? So that's a hard one.
So the Borisov one, the one we're looking at right on the screen right now, is like, for all intents and purposes, exactly what you would expect from a comet here in our solar system. It has hydrocarbon with H and C on it that might have come from like some sort of carbon, nitrogen, hydrogen mix. So it has similar chemicals. It has a similar color. I showed a bluish color, but that's actually not real. That was just put on the image by Hubble. This is a Hubble image here. This is just one filter, so it's really just gray. You don't have any color information. The actual color of this comet is somewhat reddish, which is sort of similar to the comets we have here in our solar system. In fact, the overall story of Borisov, 2I Borisov, is that it's basically like what you would expect for a comet here in our solar system. Oumuamua does have some differences, as like it didn't light up the same way. It didn't create a coma and a tail the same way, but it's both like comforting and illuminating that an object that forms around another star, it probably formed around another star and then was kicked out and came to us in some way, would be formed with similar compounds in a similar way, and so it creates a similar object. So of the two objects that we find one that's similar to stuff here and one that's not similar to stuff here. So it's kind of like a 50-50 chance right now.
Exactly, and it is obviously quite hard to get very good measurements of their compositions. And we just had one other question coming in from YouTube about trajectory, and this might be a good way to make a distinction between comets that we know about in the solar system and these objects. So the question was, can any comets change trajectory and turn around? And I'm, of course, reminded of some of the periodic comets we have, which you showed those beautiful graphs of these objects shooting out of the solar system. That might be a nice little contrast to make between our sort of traditional comets.
So can any comets that we have make any weird, there we go, any weird changes? Yeah, comets can definitely have their orbits changed. What's a great way to start this? So out beyond Pluto, there is a good word for it is a reservoir, but really it's like a cometary belt around the sun. Just like we have the asteroid belt around the sun that's in between Mars and Jupiter, we have a cometary belt that's out beyond Pluto, or well, actually Pluto's part of it. And all like chunky icy things that are hanging out way out at the edge of the solar system, and they for the most part go in roughly circular elliptical shapes around elliptical orbits. But if they get close enough to each other, if you can have a chance encounter with a large object, you can change your orbit. Gravity will just from the two objects will make them change their orbits. And what we think that's one of the ways that we get periodic comets. So a comet will at some point in its history had its orbit changed, and it'll start plunging towards the inner solar system, loop around the sun, and then head back out. But the difference is that it's a closed orbit. So it has its orbit changed, but it's still an ellipse of some kind. It doesn't have an open ending. It's fully round in a sense. Whereas what you're looking at here, this is a hyperbolic orbit. It's not closed. It's open. So the object's orbit, as you can see, it's never going to turn around and come back based on the shape that we can calculate of its orbit. So comets in our solar system, that's how we think we get the ones that come nice and close, like Comet Neowise that was just around a couple of months ago. I think that's right. And it may have come from the Kuiper belt, the cometary belt out where Pluto is. But it's never going to leave the solar system. It doesn't have enough energy to escape.
That's a wonderful answer. So I think just one more from one of our crew, actually. Shannon, I believe you've got one more question slated as well.
I do actually. I have a quick question. So I was doing some research on Oumuamua, and apparently it has a slightish reddish color. I was wondering why this is.
That is a good question that I don't think I have a great answer for. I know that objects like this tend to be redder. It could be related to, maybe actually, Dr. Hyde, you might actually have a better answer for this than it's like asteroids and comets tend to have reddish surfaces.
Yeah, I'm actually reminded of some of the discussion of the colors they found on Pluto when they did the imaging from that with the icy deposits, which do show up with a slightly reddish tinge. And it's worth remembering is, all of the images that we have of these objects are generally artists' renditions, because the actual pictures we were able to get back are so blurry we can barely just make out that there is an excess in a particular color. So we might just be seeing something like one of those icy deposits that are found on Pluto or other bodies in our solar system, but it would be quite hard to tell without getting a little bit of better resolution on the object.
Sorry, that's a hard question. I'm not 100% sure why, but yeah, there you go.
Well, whenever you see colors, you're never quite 100% sure what's causing them. We talk a lot about color excess in astronomy, but if it's not a star, we might not be able to tell you what's causing that color. And actually, even if it is a star, in some cases, we still have a little bit of trouble getting through to it. So we do have time for a little bit extra because, of course, we're looking for trying to improve our live images. I just have to actually move the telescope shortly. So we're going to try for Saturn again, and I'm going to actually task our crew here with Professor Rogerson to tell you one additional interesting fact about Saturn while I adjust the dome of the telescope.
I got so many. So
all right, you go first.
Okay, I'll go first. So I've been thinking about the rings a lot lately. And it's really interesting to think about what they're made of. So the rings are made of ice. We get that. It's mostly water ice that's floating around in the rings. But what I'm really more interested in is like, how big are those things? So there are lots of scientists that go and using data from like Cassini and from Hubble and from others, trying to figure out what the real composition is. So how much big stuff is there? How much little stuff is there? The going understanding is that the rings of Saturn have a lot of little stuff. So we're talking things like the size of sand grains, or maybe a little bit bigger, like pebbles. Lots and lots of that stuff. But you might also run into things that are around the size of like a house, or maybe a bit bigger. But even more interesting is that they found in these vast, huge rings, these little propeller shapes. And there's some really great images you can find of them, where there's these little tiny mini moons or moonlets that are sitting in the rings and have made these warped little features pushed around the rings themselves to create these little propellers around them of debris. And so you're looking at like ranges of objects from the sand grains that you can hold in your hands to the sides of a house, or even bigger with these little moonlets. Yet all within a incredibly flat ring system, as much as thin as 10 or 20 meters. So these things, like, imagine that the largest thing that's in there, like a house or an apartment building, could be like 20 meters high, and that would be as big as the rings are thick. And that's an incredible thing to think about.
All right, folks, we're just heading over to Saturn now. I believe I've been able to put the live images over onto our YouTube channel. You should be able to see the planet Saturn. So as you can see from earlier tonight, if you're watching the beginning of this broadcast, we had lots of clouds which have moved away. So can everyone see Saturn?
It looks incredible. Just like I said earlier, I'm flashing back to my undergrad. Maybe I should turn my video off, eh?
Well, you are the guest speaker, but yeah.
Oh, I can keep it on. Okay, sure.
All right. So as you can see, we have a substantially better picture of Saturn now that some of the clouds have moved. We had this on earlier tonight, and you could just barely see the rings, but now we're actually seeing quite a lot of detail, and more of the color is coming through as well. It is, in fact, a wonderful sight here. Very happy that some of the clouds have actually moved out of the way for us. Now,
I believe Quentin said he had something interesting to share.
Go ahead, Quentin.
One interesting thing that I learned about Saturn's rings is when they were first discovered, when we first developed the telescopes that were able to observe the rings, we didn't quite have the resolution to figure out what they were immediately. So some of the early astronomers who were viewing the rings thought they might be large moons, one on each side. I believe there were also some who interpreted them as ears or like handles of some sort of large jug, which is really interesting because at this point we're used to thinking of them as these like rings around the planet, and we now know that all of the other gas giants in our solar system also have these rings as well. So we're used to the concept of a ringed planet, but it is, if you think about it, it's a really novel idea that a planet could have these structures in orbit around it. And after it was determined what the shape of them was, there was some debate for quite some time about whether they were solid or whether they were liquid or what they were actually made of. So it's interesting how back then we didn't have the intuitions for these things yet, and I just find it really fascinating how there were these questions about what the rings actually were.
Yeah, this is universe changing. This is just like finding an interstellar comet or finding an exoplanet. Like when humans started using telescopes, it completely changed what we see, what we understand our reality to be. And the fact that like when Galileo points his telescope at Venus and sees a round thing, that makes sense. We get it. The moon's round, Venus is round. That makes sense. But you point it at this thing and you see these weird, whatever they are. I mean, you have to put yourself in someone from the 1600s. That makes no sense. And I believe that they kept looking at it. So we see the rings tilted looking at us. But if you watch them long enough, they eventually get to a point where they're sort of edge on. And that gives you the opportunity to make some sort of measurement of their thickness / thinness / what this structure actually is. So once they sort of quote unquote disappear, when they go edge on, that's when they really started trying to figure out that, oh, it's maybe these rings that are around this object out there, this planet out there. Completely universe changing. It's not surprising that they had funny interpretations for it at the time.
Exactly, and it is a little bit against the idea of a perfect spherical heavens where everything is spheres and perfect geometry, because in real life and especially in astronomy, things don't perfectly add up ever.
Never.
it's never completely perfect. There's always a small deviation from circular, or a perturbation to your orbit, or all kinds of different things. And Saturn is actually a great example of that. All right, so as you can see, we are in fact watching Saturn right now.
Saturn recently got the most moons, right? Back in, it was earlier this year, I believe, that the Carnegie Institute announced that there was something like 82 moons now around Saturn, I believe.
It's been a contest between Saturn and Jupiter. The more they look, the more they find. So yep. I wouldn't be surprised if next year they said it's Jupiter again.
Yeah, probably. Can we resolve Titan at all?
If we turn up the exposure time, we'll saturate the planet a bit, but we will be able to see the moons a little better. So the advantage of this over a traditional eyepiece is, in fact, that I can actually ask it to look a little deeper. So I'm just saturating a little tiny bit on the eyepiece to see if any little moons pop out. It would be, I'm not sure where Titan is in the orbit, but I don't think we're seeing it through the eyepiece. So
yeah, I'm not seeing it.
This would be a case for using the proper CCD camera and taking a lot of exposures, because that's really where you get the big detail pop when you take many exposures of an object and add them up to really increase your contrast. So we're just getting the normal view through the eyepiece, as it were.
Titan is my favorite moon in the solar system by far. It's such a weird place. It's an object that has an atmosphere. Like no other moons have atmospheres. It's incredible.
Well, we are getting just a tiny bit of clouds back in the sky here. But we will keep battling it out for everyone, because I know how exciting live images are, and we have been getting so many cloudy nights. I really want to try to show as many live images as we can possibly get to tonight. All right, so I'm just going to hop over to Jupiter real quick and see if we can get one more picture of Jupiter to come through. And by then, so if anyone is watching in the east near York University, you will see hopefully a red star. The clouds on the horizon are just blocking us at the moment. It's a little bit of a conspiracy. Okay, so I'm just going over to Jupiter. You can see the telescope's moved, and because Jupiter is brighter than Saturn, the first thing you see is a bright disk of Jupiter with some big moons. So this is the Galilean moons, a direct competitor to Professor Rogerson's favorite. Also very fun.
All four are there. Does anybody have any idea? I put challenge to anybody who's watching to find a map of what moons are which right now, because there's probably a website that'll track it. They go around pretty quickly, so they change night to night. But someone out there could probably tell me what moons those are.
Yeah, there is a sky profiler from, sorry, I just moved the mouse on the telescope computer, but there is a sky profiler from the Sky Telescope, which will tell you which ones are which. Unfortunately, I can't go there or we'll lose the picture, but if somebody else wants to hop over and look at Jupiter, that will tell you which one is which. Obviously, the farthest one away would have the least likelihood of being Io, which would be the closest to Jupiter.
That makes sense.
So we'll just go ahead and put up the process of elimination right here.
Okay, I'm trying to find the thing you're talking about, but I don't know where it is. Sky Profiler.
So you want to look for Sky Profiler Jupiter. There's one for Jupiter, Mars, Saturn, to show you what's what in the sky. There's actually a few apps that will do that.
How How have I never heard of this before?
All right, so I'm just going to increase it a little bit so you know that we don't see the bands of Jupiter anymore. And that's because I am oversaturating it so that those moons will pop up. If I decrease the exposure time again, what will happen is that Jupiter itself will be less bright, less oversaturated, and the moons will not be as visible because the moons are so dim compared to the rest of what's going on.
Okay, I think oh wait, no, never mind.
So perhaps we'll leave this up as a little bit of a challenge.
Oh wait, I got it.
Oh, you got it?
Okay, so Ganymede is that one that you have your mouse on right now.
Yep.
And then Io is the next one right there, yep. And then Europa, and then Callisto.
Ah, so Europa's all the way out here.
Look at that.
This is a little bit of a projection effect because, of course, you know, this is three-dimensional space and we're just seeing a two-dimensional view here. So if I then go ahead and decrease my exposure time a bit, what will happen is that eventually the moons will become much less visible and we'll get more of a natural eyepiece view.
So you know what I love about these Galilean moons, these 4 moons, is that they're all so unique, like incredibly so. Like Io is like the most volcanically active object in the solar system. It is like exploding. It has these huge shield volcanoes on it, and it's just constantly resurfacing itself. It's mind-blowing. And that just itself, like if you had one moon like that and around Jupiter and that was it, that'd be interesting. But then you have Europa, which is this ice world with ice all around it, with below which is this massive ocean of liquid water, which is super interesting. A little bit of outgassing going on. And then Callisto, I believe, no wait, is it Ganymede might be the largest moon in the solar system. And it has a whole bunch of water on it. And I can't remember, there's something interesting about Callisto as well. I'm forgetting it all, but the moons are so unique and so interesting.
Exactly, and as you can see, once I decrease the overall brightness, this is pretty much what you would see through the eyepiece of the telescope. So this is our regular eyepiece cam, and you can just, if you've got really good eyesight, you can kind of see the little smudges around. That's all the light that you would really be getting from the moons. They're not super bright because they're so much smaller than Jupiter. They reflect less light back to us. But now we can see, compared to when we first started this broadcast, we have a much better view of the bands of Jupiter now.
That is an incredible image. This telescope knows what it's doing. Dr. Hyde knows what she's doing.
Well, we certainly try here. So speaking of trying, I am going to try one more time on the eastern horizon. While we have our live broadcast going, we are going to go just slightly over time tonight, but we're going to give it a try for Mars. So once again, I have to move the telescope.
Let's do it.
So everyone, please say your favorite Mars fact. Jesse, you go first.
My favorite Mars fact. Oh my gosh. Okay. All right. So what I find really, really weird about Mars is, so Mars is half the size of Earth. But it almost has the exact same length of day. It's not exactly the same. It's our day is 24 hours and its day is 24 hours and like 40 minutes ish. So it's slightly longer, but that is like an incredibly random fact. The rotation rate of a planet is completely dependent on how it was formed, what hit it, what was around it while it was forming. And for the planet Earth and the planet Mars to have a 24-hour day, almost exactly the same, that's wild to me. Quentin.
One really interesting fact that I remember, I don't know why it fascinated me so much, but I remember being really surprised when I found out that Mars's red color is because there's so much iron oxide in its soil. It just kind of, I don't know, it's something about the fact that that's the same compound that's responsible for rust on Earth and that Mars's soil is essentially just full of rust. And I believe that's also the same compound that's responsible for red soil in like PEI as well. So
I believe so, yeah.
Yeah, so it's just interesting that it's even though it's like a completely different planet, we have similar effects here. And it also speaks for the fact that it also speaks for like speaks to the fact that obviously you need to have a decent proportion of oxygen in order to even generate iron oxide in the first place. So it's a really interesting fact. I've always loved that Mars is essentially red because it's rusty.
Yeah, you would need a large amount of oxygen. You need to oxidize. The iron needs to oxidize. Iron normally is this dark, I don't know, metallic-y color, but it needs to oxidize to make it red. So yeah, where'd the oxygen go? I don't know where the oxygen went, but it apparently had some in the past. Shannon, do you want to jump in? Or do you want me to say it? Well, Mars is the only place that we visited with robots, that is. Of course, the only humans have gone to the moon, but the amount of robots that we've sent to Mars is incredible. And there's one en route at the moment. Perseverance is heading to Mars. It's going to land in Jericho Crater, and it's going to try and figure out if life exists there now or in the past. More looking for in the past, and like fossil evidence of possible life. But it's also brought with it a small little drone, basically. So on the bottom of the Perseverance rover, there is a drone attached, a little mini helicopter that once the Perseverance rover lands, it'll drop off the drone, it'll like release it from the bottom, and then it'll drive away, and then they're going to unfurl the rotors and try and fly on Mars, because why not, right? If you're going to go to Mars and with a bunch of different rovers, you might as well at least try and fly on Mars. So they're going to try and do that. Do you think, Quentin's wondering if they'll think we'll have astronauts on Mars in our lifetime? Well, I certainly think so. We're going to see astronauts orbiting the moon by 2024, 25. And that's the first step. Getting onto the surface of the moon is the next step. You'll probably see that before the end of the decade. So by 2030, we'll see people on the moon again. It is definitely possible that we'll see some people walking on Mars in our lifetime. I'm really looking forward to it, because I just missed I missed it by a lot. The moon walk. Most of us missed all the walking on the moon. So I want to see something like that. I want to be a part of that global phenomenon of people walking on the moon or people walking on Mars. It's going to be incredible.
Yeah, let's go ahead and agree with that.
Yeah.
So we are battling one. It's a little bit unlucky here at York University. There's just one cloud in the way of Mars at the moment.
I think I saw it.
Yeah. So Mars has been winking in and out behind the clouds. So I've been trying to sort of cajole it out. We do have, of course, in theory, we can stay up here all night.
We should do that. Now, I say that from the comfort of my own wonderful home, and you there in the observatory in the dark. But
well, I do have to get the train home before the train stops running, so there's always that. Of course, I just am going to try checking the alignment on the dome one more time here for Mars. It is tantalizingly close. There's just this one cloud in the east. So if you've got your GPS looking at east for us, wish us luck. Now we're going to try one more time, and this is generally how we do it in astronomy. You just keep poking around to see if you can get your target above the cloud. Of course, in a live YouTube broadcast, it's always you have to be a little bit lucky as well. So I'm just going to adjust one more time on the dome. And yeah, just in general, so that you know, for Mars, actually this one I can put up for everybody. This, I'm just going to put up in the window here. This is the Mars Sky Profiler. So this is the Sky and Telescope Mars Profiler. If we're able to point towards Mars today, it will actually get us a different view of Mars than what we were showing on Monday. So in our Monday night broadcast on online public viewing, we actually saw Syrtis Major in the middle of Mars. And that's because different faces of Mars will be apparent to us here on Earth with different times and days and things, because Mars rotates. So Mars goes around the sun, but it also has its own day and night. So it spins. And Earth spins, which means on Earth's night, when we're looking towards Mars, we can see different effects on different nights. So what Monday, Syrtis Major was kind of showing up in the middle of Mars. Now it's all the way off to the edge. So if we are able to get a clear view, we'll actually have a nice clear view of the Utopia area. So I'll just leave this up as a little bit of inspiration. If you want to, you can absolutely talk about how some of these dark albedo features look a little bit like canals.
Before we get to that, Shannon's going to get a drop in a little bit of Mars facts.
I am sorry about earlier. Professor Rogerson called on me and my Wi-Fi decided to quit on me. But I wanted to say that Mars is actually named after the Roman god of war. It is the second smallest planet in our solar system, besides Mercury, which is smaller. But most people actually think that Mars is much similar in size comparison to Earth, when that's not actually the case. Venus is much closer in size to Earth than any other planet in our solar system.
Also, fun fact to go along with that, Shannon. So Roman god of war, the Roman god of war, yes, the Greek god of war. So Romans pulled from the Greeks, but the Greeks based it off of the ancient Babylonian god of war, Nergal. So when the Greeks started conquering everywhere, they went down and they borrowed a lot of sky knowledge from the ancient Babylonians and from the ancient Egyptians as well. And what it appears to be is that the Babylonian god Nergal was their god of war, which got pulled into the Greek mythology as well. Really interesting.
Well, thank you for that fun fact.
Yeah, a lot of so you can do the same exercise for many constellations. There's a lot of constellations that we use, like the zodiac constellations originated in ancient Babylonia and then were borrowed by the Greeks. There's a lot of interesting stuff like that all over ancient astronomy. Quentin, you wanted to oh my gosh, look, wait.
Dun, dun, dun.
Oh no, the moon is there.
We got it. We finally got it. So it's all been worth it, folks. If you stuck with us tonight, we have finally managed to pull Mars out from behind the clouds at the Alan I. Carswell Observatory. And because this is our first sort of recorded broadcast of Mars, during opposition, I just have to say, Alan I. Carswell, the name is on Mars as well. In fact, the Alan I. Carswell Observatory comes from the Alan I. Carswell Foundation, which was Professor Alan I. Carswell back in the day at York University. And his name, as well as that of his wife Helen, are permanently engraved on a rover on the surface due to his accomplishments. So we actually have a little bit of our sort of namesake, or we're the namesake, but it's on Mars. So congratulations to everybody who stuck with us tonight for this extra long, long-winded broadcast over to Mars.
Look at that, it looks great.
It is a little hazy.
Oh yeah, it's fuzzy, yep.
We can start to see these features. So if I pull up the Mars profiler, we can kind of see that Syrtis Major is in fact at the bottom. And if we could get it a little bit clearer, we would have a shot at seeing the pole as well. So sorry to interrupt, but please go ahead with your fun facts. Was it Quentin?
I think Quentin, yep.
Yeah, I wanted to talk a little bit about how around the beginning of, like, the end of the 1800s, early 1900s, there was a bit of an infamous theory that there were canals visible on the surface of Mars. This was primarily, I believe it was primarily, the primary proponent of this was Percival Lowell. And even though a lot of other astronomers disagreed, that said that they couldn't see the canals, And there was a lot of research that was coming out that suggested that the canals, the so-called canals that people were claiming to have seen on the surface of Mars, could be explained with optical illusions. For example, if you look at some sort of object through a telescope that isn't perfectly focused, if you have any sort of point-like objects on that surface, like in Mars's case, craters, oftentimes an optical illusion will appear where it looks as if there are straight lines connecting those dots, which may have been partially responsible for people coming to the conclusion that there were canals there. But the idea became very popular in the popular culture and is believed to be part of the reason why there were so many works of fiction coming out about aliens on Mars around that time, because some of the people who were proponents of this theory said, oh, this is evidence that there's some sort of civilization on Mars. They have these huge canal systems that are visible from space. And of course, none of that was true. And we now know that there's no evidence whatsoever of any sort of civilization, present or past, on Mars. But it is interesting. And I guess it's kind of, I guess it's kind of nice that we got like famous works of fiction like War of the Worlds out of this. So even if like the science behind this was, you know, shaky at best, I do think that it is kind of, I do kind of appreciate the fact that we ended up getting so many people thinking about the idea of life on other planets, at the very least. And it really brought that into the public eye. Yeah.
It's natural. I mean, the entire act of the science of astronomy is attempting to find ourselves in space. We look up because we're trying to figure out how we fit in, right? We look up at that and we say, what the heck is that? Why is that all doing the stuff that it's doing? Why does it move the way that it do? What ways that it does? Why does it look the way that it does? Why does it have those colors? And then so like when you can get something like a point where people can latch on point like canals, we know what canals are. We build canals, and then that can proliferate through the popular culture so quickly. So it was a funny time. It must have been weird to be living at the time to hear the stories of, oh, those canals on Mars. It sounds so far-fetched now, but when you look at it, see, if we look at it right now, you can even, like, obviously this telescope is way better than the telescopes that they had back 150 years ago or so, but you can see that there's features. So like people were excited by this. Like when we look up at the moon, we see features. The moon is obvious. There are dark parts, there are light parts, but when you look at this little tiny thing that we weren't able to resolve super well and noticed features, you get excited. And I don't know, it was probably Percival Lowell really pushed it and really tried to, if you look at the maps that Percival Lowell drew, it's quite incredible to think that he jumped from the fuzzy image to straight lines. And I know you gave an explanation, Quentin, of straight lines, but his straight line network was quite intricate. So I don't know what he was thinking when he drew it, but certainly interesting.
Yeah, it is a bit of a controversy if you ever get a chance to go down to Lowell Observatory, but just keep in mind as well that this was a little bit of a self-funded theory. So he was able to kind of self-fund his research, and
but the beauty of it is that astronomy is very democratic. It's not an incredible investment to get a telescope of your own, and it's really easy to prove other people wrong.
Yes, so nowadays especially, and I would just like to say, if anybody is outside looking towards the east right now, Mars is actually very spectacular with your naked eye. It is brighter than Jupiter.
Should I take a look?
Yes, you should take a look. It is brighter than Jupiter. It is brighter than Sirius. It is the brightest star in the sky right now, and it absolutely shines red out there. So even though our images are fuzzy, it actually looks spectacular because the atmosphere is refracting that light and making it really glow. So if you're not super impressed with this one, have a look outside. This is one of the cases where naked eye observations are going to be awesome.
It is beautiful. I just took a look. I have my window right here, and I can't see. I mean, I'm inside with lights on, so I can't see much, but I can see Mars through that window, which is incredible. That's how bright it is. Quentin, there's a good question you say from the in the chat about Mars?
Yeah, it's from Abacus Express. Autonomous self-driving cars in comparison to Mars rovers. Are they self-autonomous completely? How do they know to navigate without GPS? That technology borrowed from previous Mars rovers.
Ooh, so that's a good question. They are, I mean, each generation of rovers that's been there since the early ones have gotten more and more complex. They are sort of autonomous. They're, but not incredibly so. The rover teams are very specific on where they direct the rover to drive. So they have cameras all over, like say on Curiosity, they'll have cameras all over the Curiosity rover, and they will take so many images of the area and carefully plan out where the rover is to go next. The wheels are designed to be able to deal with terrain that they can't resolve with the images, but in general, they're driving where they're being told to drive through the uplink every day.
Yeah, exactly. And there's actually people who plan out the trajectories and the paths of these Mars rovers. It's actually a team of people, and they use things like, if you have ever looked up the HiRISE camera currently going around Mars, it has very, very good high resolution imaging of the surface of Mars. So they use these high resolution orbiting cameras and things to sort of map out possible trajectories, and then they use the images from the rover itself to kind of check, and then they have to kind of give it a set of instructions, send those instructions, and then of course it takes some time to get there because of the light travel time distance to Mars, and then the rover will do however many things it said they told it to do. So that you get this weird remote control driving. It's not quite like a self-driving car. That's a little bit of different technology, I think. Now, however, we are running into the wee hours here on our TeleTube. So as you know, this wasn't an official part of our Mars opposition event at the LNI Carswell Observatory. We just snuck it in because we were sure you all wanted to see.
We had to.
We had to.
We wanted to see.
Just as a reminder, if you did not get enough of Mars, we will be pointing our telescope at Mars with a whole slide deck full of Mars facts on October 11th, 12th, 13th, 14th, and 15th. It is October 13th that is the official opposition. So this is when Mars is directly on the other side of Earth from the sun. And if you'd like to tune in for any of those nights, it will be 8 to 10 p.m., which is even better Mars viewing time. So for tonight, I am going to just say, let's go ahead and wrap it up a little bit. Because we do all have to stop for tonight. Our crew is only scheduled to be here until 8:30. So.
Oh gosh, it's almost 10 to 9.
I know. So we really do have to go ahead and move on here tonight. But I'll just go ahead and put up my my last session here. And Shannon, are you still connected?
Yes, I am.
All right. All right, just a quick shout out and thank you to everybody for joining us tonight for this extra long, slightly Mars-oriented TeleTube. Thanks a huge to Professor Jesse Rogerson for joining in for not just a talk, but also planet viewing. And Shannon, will you please give us our outro?
Yes, I will. Well, everyone, you've been listening to the AICO Carswell Observatory's weekly TeleTube broadcast, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. This host this evening have been Quentin, Parosha, Amin, and myself, Shannon, along with our guest speaker, Professor Rogerson. Thank you again for joining us and for this excellent talk. Make sure to leave any comments or questions in the comments section of the video. You can always connect with us on Twitter or Instagram with the handle at YorkU Observatory and Facebook at AICO Carswell OBS. All of our programs are free, but if you would like to make a donation, see our website, observatory.info.yorku.ca. Thanks for tuning in, clear skies, and have a good night.